Good morning, everybody. So just a quick announcement. There is a short, very short pre-lab document for you to read. It should take you like 5 minutes around there. So that was posted last night if you've seen the announcement. If you haven't, there it is. You could easily read it before the lab, so right before you show up during the lab, or in the lab itself. I'm pretty sure the lab is timed. It's a bit short this week, I think. You never know for sure. So I'm pretty sure you can get it done in less than 2 hours. It's a string and list lab. Sorry, question? I have the, no, lab 2 pre-lab. This is the correct. There's a different one? This one? Oh, sorry. So, you know what? I probably forgot to remove the section from last. Where is it? It's lab resources, right? Yeah, sorry. This is, so when I created this course, I just copied the existing course, and I forgot to delete these. But thank you for telling me, because that is incorrect. I hope you guys didn't read that. Sorry. What was this one? What did we have to do with? Oh, this is the two-dimensional one. This was 2D arrays. Do you guys want to do this lab next week? I don't know. If you want to do this lab next week, I can leave it up. But this is an image processing lab. So that one was kind of cute. This one's a bit different, though. Sorry. That is the incorrect one. That's for the one from last year. Anyway, so there is so it should take you like 5 minutes to read. It tells you about how to do a particular operation using the remainder operator. All right, so let's just to remind you what we were talking about in the last class. We were talking about lists and recursion. We were trying to solve the following problem, right? So we have an array or a list that represents a game where you start at the left-hand side, you try to get to the right-hand side, right? The number in the square tells you the number of steps left or right that you can move. And you'd like to know, can you actually starting from the 2, can you actually reach the 0 following the rules of the game, right? So starting at the 2, I can move 2 squares to the right. I can also move 2 squares to the left, but you're not allowed to fall off the end of the board. So that means moving to the left is illegal here. Right? Once you get to the 4, you can move 4 squares right, and at the 1, you can go left or right. So I'm going to go right. You get to the 6, you can't go right because you fall off the board, so you go left. Right? You get to the 3, can't go left, so I have to go right. And when you get to the 5, you realize that you can reach the 0. Right? So this board has a solution. There's actually 2 solutions, so you can look at the second solution if you want. Right? There may be more than 2. I don't remember it now. Now, the problem on this particular, with this particular game is that you run into this problem where you end up in a cycle. So if you land on either 2, you end up in a situation where you can just keep on going back and forth between the 2s. Right? So you can go in a cycle this way, or you can go in a cycle the other way. Right? Obviously, if you end up in a cycle, or you don't want cycles to be part of your solution. So if you detect a cycle, you want to discard it as a possible, you want to discard the move that leads you to the cycle, or that produces the cycle from your solution. Right? Obviously, if you have cycles, you can make a board that has no solution. Right? So this board has no solution because you can never reach the 0. Right? On that board, you always end up in a cycle no matter what you do. And even without a cycle, it's possible to devise a board where there is no solution. So starting at the 1, you end up at the 100, and now you can't go anywhere. Right? And so you'd like to solve this problem. Again, like Jump It, it's not clear how you would write a solution to this just using a loop or loops. At least it's not clear to me. Right? And so you might say, well, if I can't solve it iteratively, maybe there's a recursive solution, and there is. Right? Now, the problem with looking for a recursive solution is the recursive solution only works if you can guarantee that the size of the problem gets smaller at every step. This particular, at first glance, this game doesn't look like the board gets smaller at every step, right? So in the previous version of the game, you discarded all the squares to the left, right? So the board obviously got smaller at every step. Here, it doesn't look like you're discarding any squares, but it turns out you are, right? So if you end up in a situation where a move takes you back to a square that you've landed on before, you know that you've encountered a cycle. right? And so you don't want to use that move as part of your solution, right? So in fact, every time you step on a square, you rule that square out from the rest of the solution. So the board does in fact get smaller by 1 square at every step, right? The only problem that you have to solve is how do you indicate that the board has gotten smaller, right? And so we'll look at that in just a second. Okay, so in a recursive method, you have to define the base cases, you have to define the recursive cases, right? So in the recursive, you can start either way. Sometimes it's easier to devise the recursive cases, sometimes it's easier to devise the base cases. I'm going to start with the recursive cases in this, for this problem. Right? So if you can move left, you want to try moving left and see if the board is solvable. If you can move right, you want to try moving right and then see if the board is solvable from that position. Right? How do you detect if the board is solvable? Well, you just recursively call the method itself. So our method is going to be is solvable. That's our board. So it's represented using a list. The index is the position that you are currently, the position where you want to start from. Right? So is solvable returns true if this board is solvable when you start at that index. Right? It returns false if the board is not solvable when you start at that index. So I'm going to start with the recursive cases. So the base cases will go here. So we'll come to those in a few slides. Right. All right, so to start with, I want to know, well, what's the square I'm standing on right now? Because I need to know how many squares left or right I want to go. So I ask the board, what is your value at that index? Right. Now remember with the list, the method get returns an element from the list, right? Given an index. Okay, so I'm on this square at position index. Right? I want some way to remember that I've stepped on this square before. So what I'm going to do, oh wait, let's go back one step here. Notice that the contract or the documentation for this method says that the method does not modify the board. Right? What it really should say is that it does not permanently modify the board. So when you call the method, right, when the method is finished, that board is the same board that was passed in originally to the method. Right? And that's nice because you don't want a method that changes the values of the board, right? Because then whoever called the method, they now have a modified board. You don't want that. All right, so I'm going to go ahead and change the board anyway. Right? So I'm going to call set, and I'm going to replace the current value in the board with the value -1. Right, now remember all the values in the board are supposed to be positive, except for the last one, which is 0. Right? So I'm going to use -1, a negative value, to indicate that we've been on this square before. Right? And so we'll come back to how we use that in the base cases. Right? Now you might say, well, you're changing the board and the method says it doesn't change the board. That's fine, you just have to unset the square when you're done with it. Right? So we'll unset this, we'll put it back to its original value later. And that's why I remember it up here. Okay, next step. I want to determine, can I move left? Right? If you're on that current square, right, and that's the value of the square, then the index of the square to the left is just index minus value. Right? That has to be an index, so it's valid as long as it's greater than or equal to 0. So if that value is greater than or equal to 0, I can move left. So I'm just going to try moving left. Right? So I'm going to call is solvable. Right? I'm going to pass in index minus value because that's the location of the square after moving to the left. And I'm going to pass in the current board. Right? Now notice when you pass in the board, right, the next version of the method gets the board that has a -1 sitting in it somewhere. Right? And so the next version of the method gets to know, hey, you've already been on this square before. Right? So this method runs, it does its work, right? And eventually it returns true or false. Right? You then want to test whether or not you can win by going right. So the index of the square to the right, starting from that index there, right? Starting from that position there, is just index plus value. Right? That's a valid index as long as it's less than the size of the board. So if that value is less than the size of the board, we can move right. Right? After moving right, you want to test, is the board solvable? So you just call is solvable again. Right? Again, right? This version of is solvable gets a version of the board that's got a -1 sitting somewhere on it. Right? Okay, so is solvable runs, right? Does its stuff and eventually returns true or false, right? And so now I know, can you win by moving left and can you win by moving right? If either one of those is true, right, we can go ahead and return that value, right? What we actually want to do is we want to return the value of win left, oops, sorry. We want to return the value of win left or win right, right? If either one of these is true, we want to return true. If they're both false, we want to return false, right? And so the value that we want to return is just the or of those two values. Now remember, we can't modify the board, or we can't permanently modify the board. So before I return a value, I have to unset the value at position index, right? I have to restore it to its original value. Now, when you call the method recursively, right, that version of is solvable is going to mark another square on the board, right? So here we've marked one position on the board. We call is solvable again. It's going to mark a second position on the board, right? If it calls is solvable again, that one's going to mark a third position, and so on, and so on, and so on, right? As each version of the method returns, though, it unsets a position on the board, right? So set one position here. That version is going to set a second version. When it returns, it's going to unset the second square, right? And now when this version of the method returns, it's going to unset the square that it set at the beginning. So this restores the state of the board, right? And there's one version of your recursive cases, right? Any questions about what just happened there? Anybody? All right, moving right along. What about the base case? Sorry, do you have a question about what's going on here? Oh, I'm sorry. This is an edited version of the slide. There was an old version of the slide where I actually made an explicit copy of the board. That should just be board. Thank you. Yeah. So you're just going to pass in the board. There's an old version of this slide where I copied the board every time. So if you copy the board, you don't care. You're never worried about whether or not you modify the copy, right? You don't have to do the copy, right? It's sufficient to set and then unset the board in each version inside the method. Right. I guess one of the confusing parts about this method is if you're not comfortable with recursion, or if you don't actually understand what happens during recursion, is that when you call is solvable again, it's going to change another square on the board, right? And it doesn't, if you're unclear about how recursion actually works, right, you might think, well, I'm only unsetting one square on the board. What about all the squares that this one caused to be set, right? And so the answer is that as this method returns, right, it unsets the square that it set, right? And so this really does leave the board unmodified. Any other questions? Yes?
Can you just explain again why you made one last false?
Oh, here. I have to initialize it to something, right? So you don't, sorry, technically that's not true. I could have just written Boolean when left and left it unset, right? And when you call is solvable, oh, actually that's not true. You have to set it here. If you don't set it here, right, that if statement, the condition here might be false, right? If the condition's false, we never set when left, right? And so in Java, that results in a variable when left that's never initialized, and the compiler will complain. Yeah, you're welcome. Any other questions? All right. What about the base cases, right? And so for the base cases, you have to remember there's a situation where we know the answer must be false, right? So one of those cases is when you hit a cycle, right? How do you know that you've hit a cycle? When you land on a square whose value got set to -1, right? Because that indicates you've landed on a square that you've seen before. So that, whoops, sorry, that's going to be one of our base cases, right? That's the one that returns false, right? Now, this is a method that returns a Boolean value, right? So it returns true or false. Often in these recursive methods, if there's a base, if it returns a Boolean, there's a base case that corresponds to both true and false, right? So there's our false one, right? You land on a square whose value is -1, the board is not solvable, right? There is an obvious case where you return true, right? You return true if you land on the last square of the board, right? And so there's your second base case. So those are easy, right? If the value that you land on is less than 0, you found a cycle. I want to abandon that solution, so I'm going to return false. Right? If the location of the square that you land on is the last location in the list, right? You've reached the end of the board, so you're going to return true, right? And now the rest of your method goes here, right? The recursive cases deal with moving left and right. Your base cases determine whether or not your method can terminate. All right, any questions about the base cases? Right, now, when you write these recursive methods, it's tempting to write extra base cases, right? So you might be able to cook up a situation where if there's 2 squares on the board, right, maybe there is or isn't a solution, right? You don't have to write those base cases, right? Because those base cases will be handled by the recursive cases. It's not incorrect if you add in extra base cases, but you have to make sure that these 2 base cases are covered. Right? If you're missing either one of these, the method will either never complete or it will return an incorrect value. All right, any questions on solving that problem there? Right. Again, it's not at all clear if you can solve this particular problem using a loop somehow, or loops, right, perhaps nested. The problem in these types of the problem in this particular case is that if you were to try to write a loop, right, each time through the loop you have to consider what happens in 2 separate cases, right? For each one of those 2 separate cases, you have to consider what happens in 2 more separate cases, right? Can I move left? Can I move right? Right? And so you end up with an exponential number of branches that you have to consider. Right? These kinds of problems, so if you studied binary trees, right, in a binary tree you've got 2 choices at every node, right? Often, many of the binary tree methods, you're often taught those recursively, right? It's simply easier to write them recursively than it is to write them iteratively. All right, one more recursive method, I think. All right, so this one's going to use sublist again. So I'm going to start by describing a simple problem, and then I'm going to use that to build a sorting method. So what I'm going to do is I want to solve the problem of searching a list for the smallest value in the list. When I find that smallest value, I'd like to move it to the front of the list. Right, now this one you can easily write iteratively. Right? Write a loop, find the smallest element in the list. Right? When you found the smallest element, so when you've searched all the elements in the list, take the smallest element, swap it with the first element in the list. Right? That solves the problem. I claim you can do this recursively. Right? So here's the idea. There's my original list. Right? So it contains the numbers 0 through 9. I would like to move the smallest element in that list, so the 0. I would like to move it to the front of the list, right? Possibly rearranging all of the other elements in the list, right? I don't care what happens. Like, I don't care how the rearrangement happens, right? I don't want to remove elements from the list. I don't want to change values that are in the list, right? I just want to rearrange them. So here's the idea, right? Suppose I can find the, so I'm going to ignore the first element, right? Ignore the 8. What happens if I move the smallest element in that sublist, shown in blue, to the front of the list? Right? Well, the 0 comes to the front of the blue list. Right? Something happens to all of the other elements. I don't care. Right? They're rearranged somehow. You don't exactly care what happens. Right? So what's the situation now? Well, I've got the 8 sitting here, right? The original first value. I have the smallest value in the blue list sitting here. What's the smallest value in the list? Well, it's either the 8 or the 0. Right? It's the one that I ignored at the beginning, right? Or it's the smallest element in the rest of the list. So I just compare them. Right? If the element at the front of the blue list is smaller, I just switch these two elements, right? And now the smallest element is at the front of the list, right? And so that's your recursive method, right? Recursively find the smallest element in the rest of the list, compare the first two elements in the lists, swap them if necessary. Right? And so there's the recursive version of min to front, right? So ignore the base case, right? First step, recursively find the smallest element in the list, not including the first element, right? So the smallest element in the rest of the list I can find recursively by using min to front, right? Now what list do I want to pass in? Well, I want to pass in the list that does not include the first element of the list. So I can use sublist for that, right? So sublist returns the part of t, right? Starting at index 1, going up to but not including t dot size, the element at t dot size. So going up to element t size minus 1, which is the last element of the list, right? So that recursively finds the smallest element in the list, excluding the first element. And now I do the comparison here, right? The first element in the list you get by calling get, so t get 0. The second element in the list you get by calling get, so it's t get 1. If the second element is less than the first element, switch the first and second, right? So how do you set an element in the list? Well, you call set, right? So I'm going to set the element in index 0 to second. I'm going to set the element in index 1 to first, right? And that's the recursive part of the method. How do I know I'm done? Right? So that recursive step finds the smallest element in the rest of the list, not including the first element. Right? It recursively calls itself, so it finds the smallest element, not including the first two elements in the list. Right? It recursively calls itself. It finds the smallest element, not including the first three elements, and so on and so on and so on. Right? Eventually, you reach a list whose size is either 1 or 0, depending on where you started from. Right? So if you have a list of size 0, right, there's nothing to do. There is no smallest element. Right? If you have a list of size 1, there's nothing to do. The smallest element is already at the front of the list. So if the size of the list is less than 2, you're done. Right? You can simply return. There's nothing to do. Right? And that recursively moves the smallest element in a list to the front of the list. Right? Again, you can easily do this with a loop. Right? But you can also do this using recursion. All right, so what happens if you repeat this process? Right, so I've moved the smallest element of the list to the front. So the 0 is now sitting here. Right? Something happened to these elements here. I don't exactly care what happened. Right? Let's say you get that. Right? Now what happens if I call min to front again on the blue list? Right? Well, that's going to move the 1 to the front. Right, so that moves the 1 to the front of the list, and we get 0 and 1. Right? Now, what if we do that again? So I recursively call min to front on the rest of the list. Right? Well, that moves the 2 to the front of the list. Right? And now I've got the 0 and the 1 and the 2. And if I keep on going, right, you end up with a sorted list. Right? And that's exactly the selection sort algorithm, which I don't know if they taught you or not. Right? If you've done any sorting, you may have seen selection sort. So it's one of the quote-unquote simple sorting algorithms. It runs in O(n) squared time. Right? So it's not one of the quote-unquote efficient comparison sorting algorithms, right? But it's one of the simple ones to implement. How simple is it? It's that simple. Right? Assuming you have min to front, right? You just call min to front. Right? And then you recursively call selection sort, passing in the rest of the list to sort. Right? So that moves the smallest element to the front. Right? Now recursively move the smallest element in the rest of the list to the front of the rest of the list. Right? And keep on going until you sorted the list. Right? How do you know you're done? Right? So if the size of the list is ever 1 or 0, you're done. Right? And so another way to write that, instead of putting in an explicit base case, right, I can simply say, if the size of the list is greater than 1, recursively sort the list. Right? Eventually, the sublist reaches a size of 1 or 0, and the method stops. Right? And so selection sort becomes 3 lines, assuming you have min to front implemented already. Right? And so that's how selection sort works. Often when students are taught selection sort, they're shown the iterative version of the method. Right? But if you just look at the iterative version of the method, it's not really clear what's going on in that method. Here, it's obvious. I'm going to move the smallest element to the front, and then I'm going to sort the rest of the list. Right? And so there's another example of recursion on a list, right? Again, using a sublist to help us do the recursion. All right, any questions about that? Okay, so it's unclear to me how they taught you computational complexity, right? If you were to analyze the complexity of this algorithm, right, the quote-unquote correct way to do it is to write down what's called the recurrence relation for the algorithm, right? So I'm going to cook up this function called t, right? The function is just the number of operations needed to sort a list of size n, right? And so when you look at the recursive version of selection sort, right, you ask yourself, well, what does it do, right? So t of n is going to be the number of operations needed to sort the list, right? So what does this do at each step? Well, it selection sorts a list that's one smaller than the previous list, right? So to sort a list of size n, you need to sort a list of size n minus 1, right? What else do you have to do? Well, I need this min to front step, right? So I need to move the smallest element to the front of this list. Right? So if you think about how you would do this iteratively, you'd write a loop that looks at all n elements of the list, and then you would swap the first and smallest element. Right? And so that step there, you know, takes something that's proportional to n steps. Right? So we say that takes big O of n time. Right? You can solve that recurrence relation for n. You can solve that recurrence relation and show that that's in O n squared complexity. Right? Whether or not you were taught how to do this in your previous courses is not important here, right? The important part here is that this particular algorithm is in O n squared, right? If they taught you any sorting algorithms, you were probably taught merge sort or quick sort, and you know that those are in O n log n, right? So much faster than selection sort, right? All right, any questions about lists or recursion, I guess, while we're here? Okay, the good news for you is I typically don't ask you to create a recursive algorithm on any of the tests, right? So if you don't like recursion, generally you don't have to worry about it because I'm not going to ask you about it, right? This is a course in object-oriented programming, not in recursion or algorithms. All right, next lecture. Hello. There we go. Okay, so we've seen lists. Well, we've seen one type of list, right? You've seen array list, right? Now, if you've seen array list, it turns out you've also seen linked list, right? So there's a linked list type in Java. It works the exact same way that array list works, right? It has all the same methods, right? The methods might have different complexities, right? But they all do the exact same thing that the array list versions of the methods do. Java also has these things called sets, right? Which C doesn't have, right? So a set is a collection of elements where all the elements are unique. So no two elements are equal to one another. This is useful for a lot of computational tasks, right? It's particularly useful if you want to know, is there an element that's part of the set, right? So that's called membership testing, right? Does the set contain something? Right? If you have a problem where you've got a bunch of elements in a list or an array, and you'd like to remove all the duplicated elements, leaving only one instance of each element, right? You can use a set, right? Because a set ensures that it contains only unique elements, right? So take your list, put the elements of the list into a set, and then take the elements of the set and put it back into the list, right? And that guarantees that your list contains unique elements. If you want to do the mathematical version of intersection, union, or difference, that's what a set is for, right? So sets are useful for many kinds of computational problems. The frequency with which you encounter these kinds of problems, though, is not very high. Right? Okay, so the big reason you need to know how to use a set, though, is because Java's also got this thing called a map. And a map has a set inside of it, so you need to know how to use a set. Sets are not arrays, and they are not array lists. Right? So there is no notion of being able to index into a set. Right? You can't slice one. You can't get an element by index. Right? So I can't ask for the third element of a set, for example. Right? That's not yes, that is true. Right? So you can't ask for the third element of a set, for example. Right? Some of the Java sets, though, they do support returning part of the set. All right, so in Java, you've got your choice of, is the third one here? No. So you've got your choice of normally 3 different kinds of sets. I'm showing you 2. There's one called hash set. There's one called tree set. Right. So if you know what a hash table is, then a hash set is similar to a hash table. So it contains, the exception is it contains unique elements in it. A tree set is a set where all the elements are unique, but they're also in sorted order. So if you wanted to make something like a dictionary for a language, right, then a tree set might be a good candidate as a collection to store the words of your dictionary. Right. So just like lists in Java, sets are generic, so they are parameterized by the element type. Right? So just like a list, you need to use this angled bracket notation and put the element type in when you make the set. So for example, if I want to make a hash set of string, right, you write hash set, angled bracket, and then string. How do you make the hash set? Well, you call a constructor. So you write new, and then hash set in newer versions of Java, so anything above Java 7, right, you don't have to repeat the string word here. Right? You can simply write new hash set, angled bracket, round bracket, round bracket. Right? So we're calling the no argument constructor here to make a new empty hash set. Just like with lists, right, you can't make a hash set of a primitive type. Right? So you're always using the corresponding wrapper type instead. How do you use it? There's only a few basic methods with the set, so this is nice, right? So there's your constructor. Right, make an empty set. Right. You can test if the set is empty, or you can ask for its size. Right, so these are the same methods as with the list. Right, so is empty. So lists also have this method. Right, true returns true if the set is empty. Returns false if it's not. Right. How many elements are in the set? That's size. Right. How do you add something to a set? Well, that's add. So it's just like a list. Right, everything is the exact same so far. Can you search a set? Yes, it's called contains, just like a list. Can you remove an element from a set? It's just like removing an element from a list, right? You remove, and you pass in the element you would like to remove. Right? Now, if the element's not in the set, remove returns false. Right? If the element is in the set, remove returns true. Right? How do you copy a set? Well, it's just like copying a list, right? You call the copy constructor. So new, hash set, round bracket, pass in the set that you want to copy. Right? You can also copy a list here. Right? So if you pass in a list, it takes the elements of the list, adds them to the set, checking or whether or not anything is duplicated. Right? So if an element is duplicated in the list, it doesn't add it to the set. Right? So that lets you remove duplicated elements from another collection. Okay, so when you're picking between sets, you're normally choosing between hash set or tree set. Right? Hash set is very fast. Right? So the fundamental operations with a set are adding an element to a set, removing it, or asking whether or not an element is in the set. Right? And so for all of these operations, these have, on average, O1 complexity. Right? Constant time. It doesn't matter how big the set is. Right? Asking, does it contain a value, on average happens in constant time. Right? So the size of the set is irrelevant or does not matter for the purposes of how fast these methods are. Now, the problem with hash set is when you put elements into the set and then you iterate over the elements of the set, you don't know what order the elements are kept in. Right? And so if you add something else to the set, the order might change. Right? So the iteration order is never guaranteed by the hash set, which can be inconvenient if you need the elements to be ordered in some way. If you need the elements to be ordered in some way, you typically pick tree set. So tree set is the set that keeps its elements in sorted order. Right? You can change the definition of how it sorts. Right? Its add, remove, and contains are fast. Right? They're in O log n complexity. Right? So the double the size of the set, right? You increase the amount of time needed by 1 unit. So that's pretty good. Right? But it's still slower than hash set. So if you need your elements sorted, you're probably going to pick tree set. If speed is the most important, which is usually the case, right, you're going to choose hash set instead. There is a third kind of set which is occasionally useful. So there's something called a linked hash set. So it's fast just like hash set. So it's O1, same complexity class for add, remove, and contains. In practice, these are very slightly slower than hash set, because this thing has to do some extra work. Right? So linked hash set guarantees that the elements are kept in the order that they were put into the set. Right? So iteration order is guaranteed to be identical to the order in which the elements were added to the set. Right? So this lets you keep some kind of order over the elements of the set. Right? The problem is the way this does this is that it basically keeps a linked list of the elements. So this takes twice the amount of memory as a hash set, at least twice the amount, roughly twice the amount of memory as a hash set. Right? So it's more memory intensive. Okay, so there's no indexing for a set. So you can't write a counting style for loop to iterate over the elements of the set. The only thing that you can do is write a for each loop. Right? So if for some reason you need to do something with every element of the set, right? For each string s in the set T, do something with s there. Right? There's no indexing. This is one of the really confusing parts about the set type. Right? If you're used to arrays and lists, then you're often used to getting or setting an element by index. You have to remember that with sets you can't do that kind of thing. Right? That's not what they're designed for. All right, so one of the things it's designed for is to ensure uniqueness of elements. Right? So suppose you have a list. I want to find all the elements that are duplicated, so all the elements that occur one or more times. Right? You can use a list to get rid of all the duplicated elements. You can use a set to get rid of all the duplicated elements. Right? So imagine that you have a list of account names. Right? So I'm doing some work for my course, and I've got a Java program that reads in everybody's email address or student number or something like that. Right? Maybe I'm doing that for multiple courses. I would like to know the number of unique students. Right? So how do I do that? I take my list of IDs of my student accounts, right? Pass it to the hash set constructor. Right? That makes a hash set containing the elements in the list. Right? So it adds each element of the list to the set. Every time it finds a unique a duplicated element, it does not add the duplicate to the set. Right? So that gives you the set of unique account names. Right? If you want them sorted, right, well, you can do that too. Right? Make a tree set instead, right, and pass the list to the tree set. Right? So you can copy or filter out a list by using a set. If you want to keep the same order of the elements that were in the original set, just removing the duplicates, you can use a linked hash set instead. Right. Okay, suppose you want to find the duplicated elements. Right? So I don't want to just get rid of the duplicates. I want to know what elements were actually duplicated. Well, you use two sets. Right? So I'm going to make a set of the unique account names. Right? Every time I find an element that's duplicated, I'm going to add that to a second set called duplicate accounts. Right? So start out with two empty sets. Right? loop over your list, right? So remember, CS account is just a list of account names. So I'm going to loop over the list now, and I'm going to try to add each account to my set of unique accounts. Right? So unique account.add, that account name. Right? Add returns true if that account is not yet, or can be successfully added to the set. Right? It returns false if that account name is already in the set. Right? So if add returns false, I know I have a duplicated account. Right? So just go ahead and add the duplicated account to the set of duplicated accounts. Right? If that account is already in duplicated account, it doesn't get added again. Right? Because again, it's a set, so the sets always ensure that there's no duplicates. Right? So there's an example. This is a picture of what's going on. Right? I've got a bunch of made-up account names up here. Right? I would like to know what are the unique account names and what are the duplicated account names. Right? So these are both sets. I'm going to iterate over that list. I'm going to try to add each element to the set of unique accounts. Right? So the first element in the list, this set's empty, so it successfully gets added to the set. Second element, right? Well, that account name is not yet in the, that account name is not in this set, so it gets added, right? That account name is not in this set, so it gets added, right? Not in this set, so it gets added, right? When you get to this element here, it is in the set, so when you try to add it to the set, add returns false, so we take that element and put it into the duplicated accounts instead, right? So that one's already there, it goes here instead. Right? The next element, well, it's already in the unique account set, so it goes into the duplicated account set. Right? And there are your two sets of unique account names and the ones that are duplicated. Okay, the set union. So the set union is the set of, the union of two sets are the elements contained in both sets. Right? So suppose I have a set containing the accounts of students who completed one assignment. I've got a second set of the students who completed the second assignment. I would like to know who completed assignment 1 or 2, right? And so that is an example of the union. Right? So the union method for sets is called add all. Right? So S1, add all S2, transforms the set S1 into the union of S1 and S2. Right? So in other words, it takes all the elements of S2 and tries to add them to S1. Right? After doing that, S1 contains all of the values that are either in the old S1 or in S2. Right? So if I want to know if S1 is the set of students who completed assignment 1, S2 is the set of students who completed assignment 2, I would like to know who completed either assignment. Right? I make a set by copying S1, and then I add everything from S2 to the new set. Right? And that gives me the set of students who completed either assignment. If you just wrote S1.addAllS2, that changes S1. Right? In this particular case, I don't want to change S1, so that's why I made a copy up here. So here's the either assignment. This is what happens when you, this is what happens when you make a copy. Right? So this set here is going to be the set that contains the students who completed either assignment. So this set starts out as a copy of S1. Right? And now I'm going to try to add each one of these to here. Right? So that name is already in this set, so it doesn't get added. Right? That name is already in this set, so it doesn't get added again. Right? That name is not in this set or this set, right? So it gets added. And that name was not in this set, so it gets added. Right? And now that's the set of students who completed either one of these two assignments. Right? So that's the set union. Right? You can do the set intersection as well. Right? So the set intersection is the intersection of two sets are the elements that are in both of the two sets, both of the sets. Right? So again, I have the set of students who completed assignment 1, set of students who completed assignment 2, I'd like to know who did both assignments. Right? So that method's called retain all. Right? So S1 retain all S2, right, keeps changes S1 so that it contains only the elements that are also in S2. Right? So it transforms S1 into the intersection of S1 and S2. So I want to know who completed both assignments, copy the first set, and then call retain all, passing in the second set. Right? And that tells you who completed both assignments. So back here, right, that's the set that's going to contain the students who completed both assignments. Right? So I'm going to start by copying that one. Right? Okay, so you're going to iterate over this set here, right, keeping any of the elements that are in this set. Right? So SP Kuma is in the second set and it's in this set, so we're going to keep that one. Right? D Parrot is in that set and it's in this set, so we're going to keep that one. Right? That name is not in this set, so nothing happens. Right? That name is not in this set, so nothing happens. Right? You're now going to compare the elements from this set to that set, right, and remove those. Right? So that's there. That's there. This one is not there, so you're going to remove it from here. Right? This one is not in there, so you're going to remove it from here. Right? And that produces that set there. Right? And finally, there's also the set difference. Right? So the difference of two sets are the elements that are contained in the first set. Sorry, the S1 minus S2 gives you back the elements that are only in S2. Right? So I have the set of students who completed assignment 1. I have the set of students who completed assignment 2. I want to know who only completed assignment 1. Right? So what did I say before? The difference of two sets is the ones S1 minus, sorry, it's the ones, it's the elements that are only in who completed assignment 1, who completed only assignment 1. Right, so you want to remove all the elements that are in the second set. Right. So remove all computes the intersection, S1 minus S2. If you want the other intersection, S2 minus S1, you have to flip those two arguments. Right. So it's the exact same thing. You copy S1, and then you call remove all passing in S2. Right. So who completed only assignment 1? Right. So you start with a copy of S1. Right. Now you start to look at S2. Right. So SP Kuma completed assignment 1, so we're going to remove them from here. Right. D Parrot completed assignment 1, so we're going to remove them from here. Right. They did not complete, they completed assignment 1, but they're not in here, so nothing happens. Right. They completed assignment 2, but they're not in here, so nothing happens. Right. And you're left with those two names there. So those are the two students who completed only assignment 1. Right. And that's the basics of using a set. There aren't many methods for sets. Right. The three fundamental methods are add, contains, and remove. Right. And then there are the operations that are unique to sets. Right. So intersection, difference, and union. All right. Next lecture is going to be maps, and then we're going to start creating our own classes after that.